Okay, welcome to PlayBASIC. This is not really a tutorial, I just want to have a bit of a mess around, so to go over some things. I might look at some of the sections in the forums if you haven't had time to check them out. The forum is like most forums, it's geared towards members, so the idea is that you would sign up and then you're given access to more and more material the more active you are actually. So people who don't post haven't seen a whole bunch of this stuff. But one of the main areas that people want to access and get into straight away is the source code area, which is just a giant board full of pretty much all kinds of weird and wonderful bits of source code, which I've posted most of this stuff here, but you're welcome to come and post your thing on here as well. Please do. Certainly makes my life easier. Often I sort of write things for people where they sort of ask and you sort of go, oh, well, okay, that's cool, I'll give that a go. You have a much higher success rate of asking me to write a tutorial or do something for you if you're active in doing something. If you're not active, then don't bother asking, because basically I don't have the time to do your homework for you. I want to have a look at something that was written a long time ago now, June 2008, and this is the crash course in program optimization. I'm not going to go through everything here, but this is a worthwhile section of the board to read. Going through, starting off giving a bit of an introduction I should say, talking about micro optimizations versus method optimization. Gives a bit of example here about, the examples about comparing the speed of it, sending a message from one person to another. One person might choose to do it by carrier pigeon, someone else chooses email, and it's no surprise which one gets there faster. The point it's trying to make is that when choosing the right method to approach a problem is very critical. You know, the picking the wrong method and sticking with it you often end up with programs that don't run very well or have problems dealing with more and more characters, or more complexity in the game, I should say. Okay, fair bit of stuff there, sorry about that, but we're just going to kind of flip down to hear some of these examples. So a couple of tips here. We've got variables faster than array and type accesses. Yeah, there you go, a bit lispy. This is the way I talk anyway. So one of the things that the runtime is really biased towards is that it's biased towards simple data structures. So the simpler you're reading from something, the faster it is. So the variables they're the simplest components or simplest types of data inside the runtime. So it stands to reason that if you have a loop like this bit here, this is perfectly legitimate code, nothing wrong with it really. It does perform the task it's meant to do. It works, in other words. But see all these, how we're accessing the same structure over and over again. And we can use some mathematical shortcuts there to remove some of that redundancy. Like I'll just cut this part here into into the PV page behind us. That's a bit of code I want to show you in a second. That's I find really frustrating, some of this stuff. Okay, so here's this little section of code. It won't run because we're missing the declarations of these types. But what you could do is you could just go x plus equals, get rid of this thing here, speed, a version of PB you have, the compile time optimizer will actually optimize out a lot of these array accesses. But can't get rid of all of them though. So I've got rid of a couple there just by rearranging, by using a better operator, which is the addition with assignment. So what happens is this value here and this value here are added together, and the result is stored in here. Same as here. So it's the same as going this equals this thing plus that thing there. Same thing. Now, if you think about what happens with an array access, we've got the index within the array we're trying to pull from. We've also got the field there as well. So let's say that every time we pull from an array, the runtime has to do 10 things to get that one piece of information out of that structure. There's also got error checking as well. It's going on. A lot of complex things are happening just to make that bit of code run. So I'll just change that code back to our simplified version. We'll count up how many operations we think are in this loop. Let's say the first line there we've got one array access. We're going to write to it, so it's 2, 3, 4, 5, possibly 6, 7, and 8. So there's potentially 8 array accesses required for this loop for every character that's in the array. The loop says I want from 1 to 10, but what happens if we have like 1,000 of these things? That's a lot of work for the runtime to do. So getting back to our point down here, it shows one loop and it times that out and gives you an average performance. The altered version stores our results in temp variables to get rid of some of the array access. You see here, so we're doing this thing here plus that and storing the result in a variable because that's the smallest, simplest thing inside the runtime. Uses that variable to compare against the screen width, apparently, the screen height, and then once we're done modifying or comparing that variable, we then write it back to the structure. So if we modify this bit of code here to do that, let's just do it like this. We'll pull that out for a second. We'll just go, so it's x position is equal to that, y position equals to that. Then when we see any x references here, we can just do this comparison. And the y is the same thing. I think before we said, or I said there was 8 potential array reads. So I've got this down to since we've pulled that data out of the structure and store it in a variable. Once we're finished with it, we've got to make sure we write it back. Now, what I could do, well, I was thinking I might not need to do that, but you will need to store them back there every time anyway. So anyway, now we've got 1, 2, 3, 4, 5, 6. So, and the cost of reading from this array, let's say it's 10 times slower than reading from a variable. So obviously this version of that particular loop is much quicker. Let's go back to the forum. So it's kind of one of these things that should be sort of obvious to people. If you have a loop that's accessing a typed array or any array hundreds or thousands of times, and you notice yourself, oh, hang on, I'm reading this data out, doing something simple to it, writing back to it, then that's a good candidate for just storing the values in variables while you deal with them, and then once you've made the modifications, then storing them back if you need to. And for me, it makes it a lot cleaner to look at. But that's pretty subjective, I guess. Let's go back here. So calling functions in loops. This is one of my absolute pet peeves. Here we've got a really simple inner loop. It's doing nothing particularly interesting. All it's doing is calling the screen width function. So I'll pull this bit of code here out. Have a bit of a look at it. Now, I'd say every time I look at someone's code and they're talking about performance things or anything, this is what I see. I see this is a massive redundancy. The fastest things in PB and pretty much every runtime out there are variables. Okay? The slowest thing to do is call a function. Right, so here we're doing to do this comparison, PB has to call this command, get the result, query the variable, make a comparison, and then that comparison is going to generate a true or false condition if then branches on whether that's true or false. Is X bigger than the screen width? If we're doing this 10 times, doesn't matter. Who cares? But if you're doing this, tens of thousands of times, that's a massive waste of performance. The screen can never change size inside this loop. As we look down here, it shows the obvious optimization. Since variables are the simplest things for the PB runtime to read, we pull the value into a variable, use it locally, and then throw it away. We don't need it after that point. So we get this code here instead. Yep, not quite as pretty. We've got a bit of extra code there on the side, but so the first version, if we have 10,000 loops, we've got 10,000 function calls. And so I'm sorry, I don't care what language you use. If you use, C, C++, and you're doing that is terrible programming. You just shouldn't be doing it. Now in C++, and most C compilers these days, they'll solve this out for you. That if you bump up your optimization level, it'll realise, hang on, particularly if it knows what this function is in your code, if that's an external function that has no idea about how it works and what it does, then it can't. That call is going to be sitting in that loop every time. And it's very expensive to call a function, even in assembly. The classic situation, we're pushing data to the stack, clearing out the stack, depends on what language we're talking about really. But so we're doing a bit of work just to even get from here to that function, doing whatever the function needs to do, and then returning back to where we are. Crazy. You don't need to do it. Okay, so here we're talking about, I'll get off my high horse there for a second. Okay, we're talking about temp calculations. This is another common one you see. Alright, I'll pull this bit of code here out, we'll have a look at it in the IDE. So 3 lines. Again, it depends on what that test end value is as to whether we would bother to do this. If we're looping 100,000 times, you'll notice something about this inner loop. I'll just make it more obvious. A and B never change inside this loop. They're not present. Who knows what they are? So clearly what we should be doing is going, hang on, I know A and B already, so I can compute this value out. I could go, well, you know, A, this keyboard's driving me nuts. A times B. And there we have it. So in terms of operations, let's just count them out. So let's assume every time we have an operator, that's one instruction in the runtime. It's not actually true, but it's just an easy way to see our benefit from doing this. So this expression here, we could say this is we've got A times B, that's one operation. Then we've got the result of this times loop, that's 2. And then we'll say the assignment is a third operation. Plus we've got the loop increment as well. So that's 4 operations it's doing. Now the code's completely redundant. You can see that. But this kind of calculation is popped up all the time. So in this one here, we've taken our four runtime instructions down to 3. We've got the multiplication, then the result of this is written into here, plus the loop processing that needs to be done as well. Clearly you would never have a loop like this in your code, but you'd hope so anyway. Short circuiting. Depends on which variation of BASIC you look at, but PB doesn't have booleans, and so as a result it cannot do this. And a lot of old BASICs don't really have it as well. I'll show you. See, this is a dumb loop as well. A and B never change inside the loop, so what the hell are we comparing them for in here? Crazy. Now, the test code, this for loop count is really just runs the logic, some massive amount, and then just times them out to see how long one takes. So we can, by rearranging the logic, which one's going to perform better. If we have something like this gets evaluated, this gets evaluated, and the two results are then ANDed together, and there's a comparison. This compare here, or the if statement, jumps upon the result of that comparison. That's potentially 1, 2, 3, 4 operations just to do that one line, plus the loop overhead. Now, if you know the most likely case, if you know that A is more likely to be true than B, depends on your circumstances, but you could just do this. You could just break this up into 2 comparisons. We actually we can have the least likely case, or the most likely case first. It depends on your circumstances, I guess. Right, so we're actually producing more operations, but the fail code, if A fails more often than not, then this is a quicker loop than before. If A is generally true, we probably don't need it, to be honest. It's one of those things where you can restructure your loop to sort of get rid of comparisons inside inner loops. Here we've gone, same thing, we've just taken the 2 cases, made 2 if statements. This one here is not necessarily true all the time. Some variants of BASIC do this, will eliminate these things at compile time, and modern versions of PV do this all the time. Functions, functions versus p-subs. These are 2 different types of modular bits of code. Sorry, I'm looking at the wrong bit, am I? Yes, not very clever. So we've got a subroutine and some function calculation. And you can often gain speed in PV in particular by not using a function if for really trivial calculations, functions have to set up the stack, as I've mentioned before, and they do a lot of work to get to fire them up. Once you're going, the code executes just as normal when you're running inside a function, but when you exit a function, there's a bit of cleanup work that needs to be done as well. With P subs, there's not. These are basically go subs, and it's kind of moving whatever data you're passing into this thing into these local variables in here, doing this and returning back. It doesn't use the stack for that process at all. It kind of works out this stuff, sort of hard codes it in for you, which means they're generally a much quicker option for this kind of function. They look exactly the same in your code. You won't even notice. So string thrashing is a classic one, and it's less important in PV. What's the example here you're looking at? Oh, okay, yeah, this is a good one. So you'll see people who come from other versions of BASIC and they'll throw strings around. They go, oh, it's pretty slow or whatever, but they do this. Here we've got a bit of code that runs through a test string. It's grabbing the 5th character out of the test string and just one single character and comparing that to A. Who knows? Yes. Now, because mid here, see the $sign there, this means that the command's returning a string. That's pretty traditional in BASIC. You know, if you come from Java or something like that, you'd be horrified by those. Although in JavaScript you can do some really crazy stuff with command names. It's kind of fun, but still it can be quite crazy. Anyway, so what we're doing is we're grabbing this character from that string, but it's actually returning a string of it. Then we've got a string comparison, and these are much slower. Even when you compare one character to another character, it's a lot of work just to compare basically 2 bytes to each other. So in PV in particular, what you should do, you should use the mid function, which returns an ASCII character. Get rid of the $sign, and it only returns one character here. And you would do something like this if you're concerned about that. This is actually resolved for compile time, so that's really just for your convenience. And this grabs the byte at character 5 as an ASCII value, which is just the byte anyway, and does a comparison with the A character with whatever this is resolves out to be. I think it's like 64 or 96, one of the two, I forget which one's which. So this loop here is probably 10 times quicker than this one. And again, if you're doing that test enough, it's a massive amount of performance you're throwing on the floor for nothing. Disk thrashing here is another classic example. Generally speaking, drives, particularly modern drives, like to read big long chunks of data. So if you run through a file and you read it byte by byte, okay, so let's look at this function here. Kind of rushing through to get this done. Just out of curiosity, really. Okay, so we've got some file we're loading. Who knows what it is? We've opened a new handle to it, which is what read new file does, by the way. And the file handle will either be 0 or some handle for the file. We can grab, if it's non-zero, we can grab the size because we know the file exists. We'll create a memory bank of this size. and then we'll actually run through the file byte by byte, poke it into memory. Crazy. And you'll see this stuff in people's code all the time. Really, in modern PV, it's unnecessary. What you would do, in fact, it's been unnecessary for a long time. There's a command called read memory. Has a channel index, which is the file handle. You give it the address. You get the pointer of the bank. This bank in this case. And tell it the size. This does two things. This is obviously a straight machine language function, but the loader internally is optimized, has a much better optimization for reading data off drives. So it's set up to read, I forget what the size, the chunk size is now, but it's kind of a weird threshold where if you read, say, files in, it might be 60k, something like that, or 4k, 8k, whatever it is, chunks, the performance is absolutely massively improved because it's just the way optical drives work, that it's kind of bursting, it's rotating at such a high speed, the head is only over the data you want for a small portion of time. So in this loop here, what's actually happening is that this read byte means that the disk has to spin around until the head is in the right spot to read that byte. When you read the next loop, the next byte from the drive, the same thing. So it just takes forever to read the data off the device. There's really no way to improve that, and let's just start reading bigger chunks of data. Obviously, you could do like you could read long. No, I think it's read int. Caps lock's on again. Crazy thing. Anyway, this wouldn't work. We have to poke, poke the bank with the integer here. We have to move here times 4, for example, and then we have to any leftover pixels or data from the file we need to sort of sort out at the end. But doing this would be 4 times faster than reading it by bytes. Requires a bit more work on the coder's behalf though. But the best way is just to read memory. Now I've deleted that, did I? Read memory, give it the file handle, get the pointer of maybe a typo there again, yet again. Okay, the pointer. So it's less code, and the performance of that is pretty much instant. What have I done there? Keyboard's driving me nuts. So we're loading the file into a bank, and that will pretty much pull the file off the device as fast as your hard drive can do it. Now, coming back from that, towards the bottom of this, we've got a whole bunch of things on way to do smarter drawing, and there's kind of some of the same analogies are actually talked about there. There's one about the cost of pixels, for example. I've actually forgotten a lot of this stuff. You can change the number of colors and make it easier for the runtime to draw the screen. Dirty rectangle examples, which is a more advanced kind of concept, but very, very easy way. Spatial partitioning even. There you go. Some pretty weird stuff. Go to PB, for example. Have a look at this other example of code. Where is it? Is it that one? This one. This is not written in PlayBASIC, although the code looks almost identical. It's meant to be. It kind of breaks one of its own rules, really. You've got this is meant to be a pixel level collision function. So just using the rules we just kind of, or some of the ideas we just looked at before, we could make a better version of this inner loop. The outer stuff here doesn't really matter. Who cares? But these inner calculations here, particularly this inner X loop, that's the one we need to focus on. I would, although it's not actually needed in PlayBASIC, what I would probably do is I would grab this value here and pull this into, width -1. So we're going to make this routine a bit uglier, but it would perform much better. So it depends on the runtime, but I suspect most runtimes will run that a bit better. Now, there's two offenders in the middle of this loop here. We've got a lot of redundancy. If you look at the X loop, okay, that we're adding X onto all of this, which means we don't need any of this because those variables aren't changing. The width of this isn't changing, or A width isn't changing, the Y coordinates aren't changing. What we could do is we could have, we'll call it A offset. I think that's basically the offset of the pixel within of each of those. Grab this. This can be B offset. Y1 plus that. Okay. Right, so A offset, and we're just adding on X to, missed that one. B offset. Now you've got to think about how many times this inner loop is going to be processed. If the width of the image you're comparing is 100 by 100, that's 10,000 times this bit of code here was running. So we've just saved ourselves, well, 1, 2, 3, 4, 5, 6, at least 6 operations in per pixel compared to the other one. Now, still the same bit of code, still the same. We've got a bit of ugliness in here. We've got this function call, and I didn't grab the function call. I just wanted to kind of demonstrate that little bit of rearranging there. As I was saying before about functions, they have a lot of overhead for what they do. So what you possibly could do here, without thinking much about it, assuming these functions return 1 or 0, you could remap that expression and get rid of the comparison and just compare this to this. Let's read that through. So we're comparing the return here. If this is false and that's true, then that's going to be false. And then we're comparing a false against a true or a negative. If they're both 0, it would return a true, and that would be false. That wouldn't work. I think what we need to have a look at the inside of this loop, inside of that function, to work out what that's doing. Probably not a good way of doing it. You could split the operation here, as I was saying before. Though the cost of this call, it doesn't matter what these two return. right? If this is actually 0 and that's 1, then we can't have a positive. So what we should do there is split up the comparison. Probably the safest way. So we're going to get, we're always going to be calling this function here, but we're only going to selectively call this function when the outer function is true. So assuming that the outer function has more, let's say the image is mostly transparent, mostly mostly transparent rather than being solid. In other words, is mostly zeros or some other value other than 1, we're going to skip this comparison altogether. So yeah, probably should have a look at this code in here. But anyway, so we've potentially made the cost of one loop possibly about possibly about 7 or 8 instructions or shorter per pixel. That's a key point. So if you've got 100,000 pixels you're comparing, that's 600,000 or 700,000 operations that runtime doesn't have to do to make that work. I didn't want a breakpoint there. Anyway, so it's good that they break out of the code when it's actually met. But I don't want to rag on that too much. Go back to the forum. So anyway, that's a bit of a good exam. It's a good old tutorial to have a read of. You might learn a few things about optimization. It's pretty much intermediate level stuff. Look at the things up here on, got smarter logic, smarter drawing, removing redundant calculations, which is what we were talking about before there, really. That's interesting. It's going to load another version of that. Oh, it's the same bit, sorry. So, a bunch of those, got some examples here about, some file examples there for dealing with big files, obviously. Shows this kind of method in use. Some stuff about drawing. Okay, that'll have to do for now. Hopefully this capture has worked. Has had some problems with the capturing as it's been. Alright, thanks for watching, and see you some other time. Bye.